Okay, so we've got our differential equation for d theta dt. And what we're going to do to solve this is a physicist thing we call separation of variables. So solve. Now, this is maybe the first time you've seen it, but in physics we tend to like to play loose and fast with differentials in ways that give mathematicians conniptions. I would say it's safe to say that we physicists are always giving mathematicians conniptions by the ways we do things. But it turns out that I can actually get away with treating these quantities d theta and dt as though they were infinitesimal. So, as though they were, I can treat them as though they were like finite, but small but finite. And what that means is if I treat this like an ordinary fraction, I'm allowed to actually multiply both sides of this equation by dt. If I do that as well by, so I'll multiply by dt, and I'm also going to divide both sides by all the stuff that depends on theta. And that way I'll end up with like only thetas on the left and dt and other constants on the right. So we divide by stuff. Divide by stuff with theta. That will have all the theta related stuff on one side, all the t related stuff on the other side, and our variables will be separated, hence separation of variables. So let's go ahead and do that. So what is the theta dependent stuff that I want to divide out, right? So I can only divide out by stuff that's a multiplicative factor. So I can't just divide the cosine theta here. I have to divide this entire piece there in green. So I'll do that. And that leaves me with, right, so d theta over the square root cosine theta minus cosine theta dot. And then if I shove the dt over on the other side, I'll leave this as a plus or minus square root of 2g over L dt. Okay. Anybody want to guess what we're going to do at this point? You guessed correctly. We're going to integrate this. So it turns out that this is a definite. We will do definite integrals, and I'm pretty sure this is the first time you've seen this. But what we're going to do is we're going to integrate in a physical sense. We're going to choose the limits appropriately and consistently. So what I'll sort of write this out formally. So I'll write this as, right, so now if I integrate both sides, I get, so purple, I have the integral of, so d theta cosine theta minus cosine theta naught over here, and over here on this side I have dt, I'm integrating with respect to t, but 2g over L, root 2g over L is a constant, so I can pull that out. So I end up with plus or minus root 2g over L, integral of dt, where I now have to assign consistent physical limits. So this is the part that gets slightly tricky, so to think about. So physically, right, we're dealing with this swinging pendulum, and I'm trying to analyze like between when it releases here, and I want to ultimately find one period of its motion. Now I'm gonna be a little bit hand wavy here. It turns out you might think, well, why don't we just integrate this over one full period, right? So then I would sort of start. I want the theta I start at, and that would be theta naught. And one full period later, I'd be back at theta naught. The kind of tricky thing is that this, because of the periodicity, right? If I integrate from theta naught to theta naught, I'm like integrating this with respect to theta over no interval. So that turns out to not actually be helpful. Integrating over nothing gives me 0 here. And so what I actually want to do is to integrate over 1/4 of a period. Because if I pick a quarter, so if I started from here, right, half a period is up there. So if I went from like theta equals like plus theta naught to minus theta naught, I still have sort of periodicity issues. You can maybe see how it's symmetric. Instead, what it turns out I want to do is to think about from theta naught here to down here, theta equals 0. So integrate, go from the release to theta equals 0, which is 1/4 of a period. Okay. So let's now sort of use that to assign the physical limits of integration. So if we we release it at theta naught at t equals 0, we'll integrate from t equals 0. And then we'll go up to 1/4 of the period, so that'd be 0 to t over 4. That's not so bad. This one's a little trickier. We want to basically assign our limits of integration on theta to correspond to these two times. And so at theta equals 0, at t equals 0, right? We're at, my ball's rolling away. We're at t equals 0, right? I'm at theta equals theta naught. So we have here theta equals theta naught. And what's the angle at 1/4 of a period? It's 0. Okay, we're getting somewhere, right? Okay, at least, well, we can maybe do this side. This integral's easy, right? It's a perfect differential. So by the fundamental theorem of calculus, right, I just get t over 4L. So I end up with plus or minus root 2g over L times t over 4 equals all of this, right? I'll just write that as dot, dot, dot. We're getting somewhere. The only kind of weird thing is that, right, I have now this integral going from theta naught to 0. Most of the time we like to start our integrals with a smaller thing as a lower limit. So I'm actually going to take the opportunity to flip the sign here. Okay. So I've got to erase the board, but what I'll do is I'll turn this around so I have t on the left, and then I'll flip the sign on this integral, and then we'll come right back, and we're almost done. Okay, we're almost there. So we've got this integral here on the right side, and it looks kind of nasty. If you go and like put this function into a graphing calculator, or like do something, use like Wolfram alpha to plot like the integrand, I think you'll be able to convince yourself that this integral turns out to be positive. So that's what, so because I flipped the limits around here, I have minus plus on this side. We know ultimately that the period should be a positive number. So what I'm going to do is I'm going to choose the positive square root. So I almost have the period. I now just need to go and shove all of this over. So I'll multiply by square root of L over 2G and by 4. And what I'll get is T equals 4 here times the square root of L over 2G times this thing, which I'm just not going to rewrite. I can simplify this a little bit if I remember that 4 is the square root of 16. So if I shove the 4 under the square root, I end up with square root of 16 divided by 2, which is 8. And then I get this result. I get my final result. Namely, that the period valid at all angles, and your background manual calls this T sub AA for all angles, ends up being root 8L over G times this interval 0 to theta naught d theta cosine theta minus cosine theta naught. This is our main result for today. Now you might say, well, wait a minute, well, how is this even helpful? Well, you still haven't done this integral over here. I haven't. It turns out that this integral isn't really possible to do in terms of like elementary functions. But this integral turns out to be one that is tabulated if you go and look up a math handbook, so you're probably all too young to have seen one of these, but if someday when life gets back to normal, you can come to my office and I can show you one of my math handbooks. Matt Price has a couple in his office too. He does have the hardcover of Radstein and Rizhik, which is this like Russian compendium of integrals, and it's said that the authors like locked themselves in a cabin in Siberia sometime during the 1930s, just doing horrible integrals. Anyway, this isn't a particularly bad one. It turns out this one can be written in terms of something called an elliptic integral of the first kind. Now, if we wanted to go through a whole lot more work, we could try and simplify this and like try to figure out what happens in the limit that like theta naught is not small but not very large either. But I'm not going to go through that analysis. Instead, if you're curious, ask me about it, and I can share some additional materials. Instead, what we'll do is we'll calculate this numerically. The easiest way to do this is using Wolfram alpha, which I'll show you how to use in a second. And this is what your background manual defines as integral of something that depends on theta naught. And so we get, we end up with T equals root 8L over G int theta naught. Now there's one interesting thing to notice here, right? So notice how this differs from the result for small angle. So if we have the small angle result, I'll write that as T sub small a, that's times T sub SA. We said that was 2 pi root L over G, right? Now, if this result is valid at all angles, well, these two things had better agree when theta naught is small. So that's something we'll be able to actually go and check in a second. So what we expect for small theta naught, expect, right? We have this common factor of root L over G in both of these expressions. That's good, right? But that's required by dimensional analysis. But we better expect, so the rest of this, so root 8 int theta naught equals 2 pi, or equivalently int theta naught equals 2 pi over root 8, but square root of 8 is 2 square root of 2, because 8 is 2 times 4, or that simplifies to pi over root 2. So we'll be able to go and check that. So I want to wrap up this video by showing you how we can use Wolfram alpha to evaluate that integral that we wrote as int theta sub naught. So a highly useful website for helping with math is wolframalpha.com. Wolfram's the same company that makes Mathematica, and it turns out that you can just tell it to do integrals. In our case, we want to integrate, and I'll just write this in terms of x. So I'll write this as dx divided by, or I'll write it as 1 over the square root of, we're going to work in radians. So let me just pick a value for theta naught. Let me pick, let's just say 0.2. So I'll write this as cosine x minus cosine minus cosine 0.2. I'll close the parentheses here, dx, from, we want to go from 0 to theta naught. So we're going to go from 0 to 0.2. And Wolfram alpha actually understands this. So if I hit enter, it's going to think. And look, it will have done the integral. And we have a number, right? We can check that the integrand is what we wanted. We wanted indeed d theta from the cosine theta minus cosine theta naught here, and 0 to theta naught, and we have our answer. And you get a little bit of a visual representation here. This is a little bit misleading because this the whole so it's showing x or theta here, but remember that the result also depends on theta naught, and that's really the dependence we care about. So anyway, so we can do this for different angles, right? So I can do it for like a bigger angle. So let's just say theta naught equals 0.5 radians. So anytime you do calculus with trig functions, you're going to be working generally in radians. If I go and do this, right, notice that my result got a little bit bigger. So what does this maybe suggest about the period of a pendulum for large initial angles? You can think about that. One more thing to look at, I convinced you earlier that we should see that for small angles, this integral reduces to, what is it, pi divided by root 2. Let's see if that's the case. So let me pick a small angle here. So let me do this from, so let me put theta naught equals 0.05. If I now do this integral, I get 2.221 something, or round that to 2.222. Let's see what happens if I make this really small. Let me make this like 0.01. So I now get 2.221. something, maybe do one more tiny value for good measure, 2.221 for something. So I think we see where this is approaching. Let's see what pi over the square root of 2 actually is. And that is indeed 2.221 for something. Exactly as we thought. So it looks like our integral is behaving the way we expect it to for small theta naught. So we've now seen how we can use energy methods to derive a general result for the period of a pendulum released at all angles in terms of a mathematical function we can calculate, or at least get Wolfram alpha to calculate for us. We now have some quantitative predictions about the period as a function of initial release angle. And that's what you're going to be exploring in procedure part B of the pendulum experiment. Take care, and I'll see you then.